Hi. What we are going to do now, that was the circuit that we analyzed. That was an exam question at the same time. After that, we have done this analysis in frequency domain. So the solution that we found was a particular solution, and that was a sinusoidal signal. Now in that simulation, we thought that if we do the simulation, I can compare my calculation result and the simulation result. So see what happens. So we are going to simulate this function, this circuit. So we've got 4 elements here. One capacitor. Take the capacitor here, and we've got an inductor. Put that inductor here and turn it a bit, and then we've got a voltage controlled current source. Put that here. But we're going to the vertical mirror, make this arrow upwards, because it is upwards here. You see here, upwards. I made it upwards. And a resistor. Take the resistor here. That's the resistor. Let me put that on this. Oh, it's going to disappear when I click anyway. Okay. So I made the model a bit like that. Here you are, so you could see it at the same time. Okay, do the connections now. So this is going to be connected to this. Okay. This resistor should be connected to this. Okay. Let's move it this way and put it here. And then move it a bit downwards. This is connected to here. And this is, so this here is connected. You see this, that is reference voltage that which is VC at the same time. The positive terminal of this one should be connected to the positive of this one. So this positive here should be connected this capacitor, this terminal. The negative one should be connected to this one, isn't it? So this is what I was trying to do here. Put that in, and I'm going to connect this one to this one. Okay. So what I have done it, this plus sign is connected to that plus. We have done all those, so let's choose the parameters now. Capacitor is 10 microfarad. It is just 1 microfarad here. I made it 10. Parameter for the dependent source is 0.1. 0.1. Okay. Inductor, it says 1 millihenry. We'll make it 4 millihenry for our case. And resistor, it says 10 kilovolt here. We're going to make a 20 ohm here. Yeah. So what is left? The source. Source, we are going to take the source from here. You see this this signal here. These are the sources area. Put that in. Sine function, sine sinusoidal function will be taken from here. So I put it here. Horizontal mirror. Then do the connection. So the parameters of this source, this is a voltage source, sine, and this sinusoidal function has got 3 parameters. One of them is the amplitude, which is 10. So I'm going to make 10 volts, that amplitude. Let's come to frequency. The frequency shown here is angular frequency. Angular frequency is equal to 2 pi f. In Proteus we've got hertz, that is F. F is equal 10,000 over 2p. So let's do the calculation here, you can follow it as well. So let me put it here. Here we could do this calculation. What we said, 10,000 10,000. I made a mistake, isn't it? So okay, clear them all. Oh, I'm going to clear them. I did. Anyway, clearer here. So I'll show it now once again. 10,000, 1, 2, 3 divided by 2 equal to this. Once again divided to pi is equal to this. 1,591, isn't it? So that means 1.5, 1.6 kilohertz. So I will put that 1591 here. 1591 hertz. Angel is 0 here, so I put 0 here. Name of our source is VS, so I'll change the name here, VS. I would like to see the properties, so I clear this. You see here you are, amplitude 10, frequency 1591, phase is 0. Forget the others. Now in here, alright. Now we transfer our circuit to Proteus now. We are going to do analysis. We need a graph. Put that graph in. We choose the analog and put that graph here. Graph. Yeah. So in that graph we can make it bigger. Take this here, make it capital. What we have forgotten, put which voltages that we are going to measure. So we are looking for the capacitor voltage. So I put that probe here, connected to here, and this voltage, name it VC. This is the voltage that we would like to calculate. We already calculated this in frequency domain. Now I would like to observe it here. So we've got to add those two voltages. VS, I put here on the left hand side. VS, okay. And another signal that I would like to observe is VC. I'll put it on the right hand side. Okay, and we're going to run it now. So we've got a problem. So what happens, I'll explain it to you now. What happens is this. You see here a green area here. Why it is so green? Because the final time that we have chosen is that 1 second here. We have a signal that is the source signal, which is frequency is 1591 hertz. Inverse of this is going to give us period. So 1591 inverse of this. Where is this inverse? I'll make it capital. Inverse is this. What you see, that number here, minus 10 to the power minus 4, That means 0.62 is millisecond. So we've got almost half millisecond period. So what does this mean? In that 1 second, I have got 1591 these periods. So you cannot put all that signals in here, in this area. It is very wide area. What I am going to do, I am going to change the settings here. You see that settings. So this is 1 second. I am going to make this is 3 millihenry. 3 millihenry. Then we would see something proper now in this case. Okay. So we've got this. I'll check one more thing here. We have forgotten the ground. I should have had ground as well. I put that ground as well now here. And then run it once again. You see what happened here. This green one is the VS, that's source sinusoidal function. Source sinusoidal function is 10 volt, you see here, 10 volt, minus 10 volt, plus not minus, so 0 is here. If you look at the other signal, that is VC, VC goes almost 0, and then it jumps. It jumps to where? After 299 milliseconds, that means 3 milliseconds. After 3 milliseconds, my VC voltage is going to be 13 plus 2 million volts. That's a very high voltage. What does this mean now? The answer is this circuit is not stable. Because of this voltage, this circuit is going to burn. Now, where is our sinusoidal function? Where is our particular solution? Where is our calculations results sinusoidal function? It's not seen here. The answer is this. Proteus show us time domain general solution. General solution is equal to homogeneous solution plus the particular solution. What we have found is the particular solution. Since the circuit is unstable, homogeneous solution becomes infinite, almost infinite in very short time. That means circuit is unstable. If this circuit is unstable, my general solution, the dominant part in the solution is the homogeneous solution because it goes to infinity. So I cannot observe that finite sinusoidal function on that. I am seeing this dominant part, which is homogeneous solution. Since it is unstable, it goes to infinity. So I am observing that. I can't observe particular solution here. Later on, what we are going to do is this. I am going to make this circuit stable circuit. How I am going to make it, I'll show it later on. I am going to change this coefficient here. A small change I am going to do that. All the configuration is the same, all the other elements, parameters are the same. Just by change this factor, this coefficient here, we are going to observe that this circuit is going to become a stable circuit. When it is stable circuit, homogeneous solution is going to be exponentially decreasing functions, opposite the other one. That means decreasing in a few milliseconds. This solution is going to disappear. Homogeneous part is going to disappear because the system is stable. Then our general solution is going to be equal to our particular solution. So in frequency domain, I have found the particular solution. So I'm going to observe the particular solution that I calculated in the simulation after I changed this value. So that's going to be another video that I'm going to show you later on. So let's stop this now.